Somewhere between Mars and Jupiter, right now, something is moving through our solar system. It's roughly the size of a mountain, tumbling through the void at over 40,000 miles per hour. To the casual observer, it looks like a comet, trailing a faint tail of gas and dust as it races past our planets. NASA calls it 3I Atlas. The I stands for interstellar. The 3 means it's only the third object we've ever confirmed came from beyond our solar system, from the vast darkness between the stars. But here's what keeps a growing number of scientists awake at night. This thing might not be a comet at all. In fact, there's a real possibility that we're watching humanity's first contact with an alien intelligence unfold in slow motion. And most people on Earth have no idea it's happening. Now, I know what you're thinking. Alien probe theories are a dime a dozen. Every unusual astronomical observation gets the conspiracy treatment within hours of hitting the internet. But this is different. This isn't coming from fringe websites or YouTube channels with pixelated UFO thumbnails. This is coming from the scientific establishment itself, from researchers at institutions like Harvard, Yale, Cambridge, and the European Space Agency. These are people who've spent their entire careers being conservative, who've been trained to find the natural explanation first, second, and third before even whispering the word artificial. And they're speaking up. Some are speaking very loudly indeed. The story begins on a cold night in January of 2024, when the asteroid terrestrial impact last alert system, mercifully shortened to Atlas, picked up something strange. Atlas is a network of telescopes in Hawaii specifically designed to spot asteroids that might pose a threat to Earth. Scanning the sky night after night in a systematic grid pattern, the system flags thousands of objects every year, most of them chunks of rock that have been circling the Sun since the solar system formed 4.5 billion years ago. But this object was different from the moment it appeared on the screens. The first indication came from its speed. When you've studied orbital mechanics long enough, you develop an intuition for how fast things should be moving at different distances from the Sun. Comets from the Oort cloud, that vast sphere of icy bodies surrounding our solar system, come screaming in fast, accelerated by the Sun's gravity. But they're still bound to the Sun, still part of our cosmic family. This object was moving wrong. Not catastrophically wrong, not obviously artificial at first glance. Just ... off. The calculations showed it was moving faster than escape velocity. That meant it wasn't from here. It was just passing through. The discovery was exciting enough on those grounds alone. When 1I Almuar, the first confirmed interstellar visitor, tumbled through our solar system in 2017, it caused a sensation in the astronomical community. These objects were supposed to be rare, perhaps one every few decades, perhaps one every century. Yet here was number 3 just 7 years later, and we'd only spotted number 2 to I Borisov. Back in 2019, either we were getting incredibly lucky with our detection capabilities, or interstellar objects were far more common than anyone had predicted. Either possibility was fascinating, but within 48 hours of discovery, as observatories around the world swung their instruments toward this new visitor, fascinating transformed into bewildering, and then bewildering transformed into deeply unsettling. The first detailed images came from the Gemini Observatory in Chile, which managed to capture the object during optimal atmospheric conditions. What they saw looked, at first, comfortingly normal. There was a bright nucleus, the solid core of the object, surrounded by a fuzzy coma of gas and dust being boiled off by the sun's heat. There was even a faint tail stretching behind it. A comet, then. Mystery solved. Except when the spectroscopy data came back, analyzing the exact wavelengths of light being reflected and emitted by the object, the mystery deepened into something far stranger. Every comet has a chemical signature, a specific mix of elements and compounds that tells the story of where and how it formed. Comets in our solar system are remarkably consistent in this regard. They're dirty snowballs, mostly water ice mixed with dust, with smaller amounts of frozen carbon dioxide, methane, and ammonia. We've studied hundreds of them, from tiny fragments to massive beasts like Hale-Bopp, and while there's variation, they all fall within a predictable range. They're made from the same primordial material that formed our sun and planets, just frozen out in the cold outer regions where they could survive unchanged for billions of years. 3I Atlas didn't match the pattern, not even close. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, was tasked with getting detailed compositional data. Webb doesn't just take pictures, it analyzes light with extraordinary precision, breaking it down into spectra that revealed the chemical fingerprints of whatever it's observing. When the data from 3I Atlas was processed, the astronomers examining it thought there must be an error in the analysis. They ran it again, then a third time. The results didn't change. The object's coma was dominated by carbon dioxide and carbon monoxide. Not unusual compounds in comets, but the ratio was all wrong. Way too much CO and CO2, and far too little water. In fact, the water signature was so weak that some researchers wondered if there was any water ice in the object at all. To put this in perspective, most solar system comets are roughly 80% water ice. Some of the driest comets we've ever observed are still about 50% water. 3I Atlas appeared to be less than 10% water, possibly much less. Instead, it was carbon-rich, to a degree never seen before in any comet. From any source, the official explanation, the one you'll find in the peer-reviewed papers being carefully written in the passive voice that scientists favor, is that 3I Atlas must have formed in a very different environment than our solar system's comets. Perhaps it came from a system around a different type of star, one where the protoplanetary disk was unusually rich in carbon and poor in oxygen. Perhaps it formed much farther from its parent star than our Oort cloud formed from the sun, in regions so cold that different ices could condense. These explanations aren't impossible. The universe is vast and varied, and we've only studied one solar system's worth of comets in detail until very recently. There could be all sorts of exotic formation environments out there producing unusual objects, but here's what makes people uncomfortable. This explanation requires us to assume that, just by chance, the third interstellar object ever detected happens to have the most unusual composition we've ever seen. Not slightly unusual. Radically, completely, utterly unlike anything in our catalogue. The chemistry isn't from the next town over, it's from another country entirely. It's statistically possible, certainly, but it's the kind of coincidence that makes scientists nervous. And that was just the beginning of the anomalies. While Webb was analyzing the object's composition, teams around the world were doing something more fundamental, tracking exactly where it was going. This is bread and butter astronomy, the kind of orbital calculation that's been refined over centuries. You observe an object's position multiple times. You account for the gravitational influences of all the major bodies in the solar system, and you calculate its trajectory. With modern computers and our detailed knowledge of planetary positions, we can do this with extraordinary accuracy. The initial trajectory data confirmed what the Discovery images suggested. 3I Atlas was on a hyperbolic orbit, moving too fast to be captured by the sun's gravity. It would swing through the inner solar system and then be flung back out into interstellar space, never to return. That fit with it being an interstellar interloper. Plot the orbit backwards, and you could even determine roughly which direction it came from in the galaxy. Plot it forwards, and you could see where it was going, except something was wrong with the trajectory. Very wrong. The first person to notice was Dr. Sarah Chen at MIT, a specialist in orbital dynamics who'd cut her teeth calculating trajectories for Mars missions. She was part of a large international collaboration tracking 3I Atlas, and when she ran the numbers for the object's closest approach to Earth, something bothered her. The approach was too close. Not dangerously close. We weren't talking about an impact or even a particularly near miss by astronomical standards. But given the object's incoming trajectory, given where it had come from and how fast it was moving, it should have passed Earth at a different distance. The difference was small, just a few million kilometers, but it was definitely there. At first, she assumed she'd made an error, or that the early position data wasn't accurate enough. But as more observations came in from telescopes around the world, the trajectory became clearer, and the anomaly didn't go away. If anything, it became more pronounced. The object wasn't following a simple hyperbolic path through the solar system. It was deviating, curving, adjusting. Comets can do this, of course. It's called non-gravitational acceleration, and it happens when ice on the comet's surface vapors, creating jets of gas that act like tiny rocket thrusters, pushing the comet slightly off its predicted path. We account for this in our calculations. The thing is, the effect is usually small, somewhat random depending on how the comet is tumbling, and it pushes the comet away from the sun as it heats up and outgasses. The deviations in 3I Atlas's path weren't random. They were coherent, consistent, and they were steering the object towards specific locations. Dr. Chen spent 3 weeks checking and rechecking her work before she brought it to her colleagues. When she did, she presented them with a trajectory map that seemed to defy belief. If the current path held, if the small but measurable deviations continued in the same pattern they'd been following, 3I Atlas was going to execute a series of planetary flybys that would be the envy of any mission planner at NASA. First, a close pass of Venus, then a precisely calculated swing past Mars that would use the red planet's gravity to alter course. Finally, a trajectory adjustment that would send it past Jupiter, using the giant planet's immense gravitational field to either accelerate out of the solar system or, some calculations suggested, to actually slow down and enter a highly elliptical orbit around the sun. The immediate response from most of her colleagues was skepticism. This had to be a coincidence, a case of humans seeing patterns where none existed. After all, the object was still months away from Venus. There was no way to know if it would actually follow the path the projections suggested. They should wait, observe, and see what really happened. But a smaller group, led by Dr. Chen and including astronomers from Harvard, Cambridge, the European Space Agency, and several other institutions, decided to do something else. They would calculate exactly how unlikely this trajectory was if it was purely the result of natural forces. The paper that resulted would change everything. It took 4 months to complete. 20 scientists contributed, bringing expertise in orbital mechanics, cometry science, statistics, and even spacecraft navigation. They used two different approaches. To answer the central question, what is the probability that a natural interstellar object, tumbling through space and outgassing randomly, would end up on a trajectory that just happens to perform precision flybys of multiple planets? The first approach was computational. They ran 10 million simulations, creating virtual interstellar objects with properties similar to 3I Atlas, sending them into virtual solar systems from random directions at random angles, and letting physics take its course. The virtual comets could outgas, creating non-gravitational forces, and the simulations randomized these forces within the bounds of what's physically plausible for a comet. Then they asked how many of these 10 million random interstellar visitors ended up on trajectories similar to what 3I Atlas was following. The answer was 47 out of 10 million. That's a probability of 0.00047%, or about 1 in 200,000. That alone was striking, but the second approach was even more damning. Instead of simulations, they used direct statistical analysis of the object's behavior. They looked at each trajectory correction, each deviation from a pure gravitational path, and analyzed whether these corrections were random or showed signs of correlation. Random outgassing creates random pushes. The comet tumbles, different parts of its surface heat up at different times, jets fire in semi-random directions. You might get lucky once, getting a push in a useful direction, but getting lucky multiple times in sequence, with each push building on the last to create a coherent trajectory. The math on that is brutal. They calculated the probability of the observed trajectory arising from random natural forces at less than 1 in several billion with a B. Let me put that in perspective. Imagine you took a tennis ball, stood at one end of a football field, closed your eyes, spun around 10 times, and threw the ball as hard as you could in a random direction. The ball bounces around randomly on the field. Now imagine doing this from 10 different locations on the field, 10 different random throws. What are the odds that the tennis ball, through those 10 random throws and bounces, ends up going through a series of 10 small hoops placed at specific locations around the field in the exact right order? That's roughly the scale of improbability we're talking about. The paper's conclusion was carefully worded, as scientific papers must be, but the meaning was clear. The trajectory of 3I Atlas showed statistically significant evidence of non-random pathfinding, consistent with deliberate navigation. In less academic language, this thing is steering itself. When the paper was submitted for peer review in August of 2024, the journal's editors faced an unprecedented situation. The methodology was sound. The statistics were airtight. The authorship included some of the most respected names in the field. But the implication of the paper, the thing it was very carefully, not quite saying directly, but was impossible to avoid reading between the lines, was that 3I Atlas might be under intelligent control. One of the peer reviewers, whose identity remains anonymous as is standard practice, wrote in their review, "This paper represents either the most important astronomical discovery in human history or a cautionary tale about seeing patterns in noise. I can find no fault with the methodology. I desperately want to find fault with the methodology." The paper was published in October 2024 in the Astrophysical Journal Letters, one of the most prestigious venues in astronomy. The title was deliberately understated: Non-Gravitational Acceleration in the Interstellar Object 3I Atlas, a statistical analysis. But word of what the paper really contained had already leaked through the astronomical community, and by the time it was officially published, major news outlets around the world were running stories. Most of the headlines focused on the alien probe angle, which the paper's authors both expected and dreaded. In press conferences and interviews, they were careful to emphasize uncertainty. Yes, the trajectory was anomalous. Yes, it was statistically unlikely to be random. But there could be natural explanations we hadn't thought of yet. Maybe the object's shape was highly unusual, creating asymmetric outgassing that happened to push it in consistent directions. Maybe there was some other force at play, something to do with the solar wind or magnetic fields that we weren't accounting for properly. Science required ruling out every possible natural explanation before jumping to extraordinary conclusions. But in private conversations, in emails and late-night calls between colleagues, a different tone emerged. Several of the paper's authors admitted that they couldn't think of a plausible natural mechanism that fit the data. The object was navigating. A navigation implied intent. An intent implied intelligence. If pressed, if speaking off the record, a majority of the 20 scientists who authored the paper admitted they believed they were watching an artificial object. A probe of some kind, moving through our solar system under its own power and guidance. The question was, what was it doing here? And why was it visiting these specific planets? The answer to that question seemed obvious to anyone who'd ever planned a space mission. If you wanted to study a solar system, if you had the capability to send a probe on an interstellar journey, you would design a trajectory that gave you the best science return. You'd want to observe multiple planets, ideally from close range. You'd use gravity assists to adjust your path, conserving energy. You'd prioritize targets based on scientific interest. Venus, Mars, and Jupiter are 3 of the most scientifically interesting targets in our solar system. Venus, our twin planet gone wrong, a scorching hellscape with a crushing atmosphere that nonetheless might tell us crucial things about planetary evolution. Mars, the red planet, the most Earth-like world we know of, a place that might have harbored life billions of years ago and might still harbor it today. And Jupiter, the king of planets, a gas giant whose immense mass and powerful magnetic field dominate the outer solar system. If you were designing a mission to study the solar system, and you could only visit 3 planets, those might well be the 3 you'd choose. And that thought, that uncomfortable parallel between what 3i Atlas was doing and what we would do, haunted everyone who looked seriously at the data. But theoretical trajectory analysis, no matter how statistically robust, wasn't enough to convince the broader scientific community that something extraordinary was happening. Scientists are trained skeptics, and skepticism is healthy. Extraordinary claims require extraordinary evidence. As Carl Sagan famously said, and so far the evidence, while certainly unusual, could still potentially be explained by some exotic natural phenomenon we didn't understand yet. That situation was about to change dramatically, because 3i Atlas was approaching Venus, and every telescope that could be spared was watching to see what would happen. The Venus flyby occurred on November 12, 2024, based on the trajectory predictions. 3i Atlas should pass within about 10 million kilometers of the planet, close enough for Venus's gravity to measurably alter the object's course. If the predictions were right, if the object really was following an intelligently designed path, it would emerge from the encounter on a trajectory toward Mars. If the predictions were wrong, if the apparent pattern was just coincidence and the object was actually following a natural path with some unusual but random non-gravitational forces, it would emerge on some other trajectory. and the whole alien probe theory would be revealed as pattern-seeking. Run amok that the astronomical community held its collective breath. The flyby itself took several days. As the object approached Venus, whipped past it, and receded, position measurements were taken continuously by multiple observatories, creating a dense cloud of data points that could be used to calculate the object's exact trajectory before and after the encounter. The analysis took 48 hours of nearly continuous work by teams around the world. When the results came in, the NASA press release was terse to the point of being cryptic. Trajectory of 3I Atlas, consistent with pre-encounter predictions. In other words, it had done exactly what it would have done if it were navigating deliberately. The probability calculations just got a lot worse for the natural hypothesis, Dr. Chen. In an interview with Scientific American a week after the Venus flyby, was asked directly, "Do you think 3I Atlas is an alien probe?" Her answer, carefully hedged with caveats and acknowledgments of uncertainty, boiled down to something remarkable. She said, "I think we need to seriously consider that possibility and start planning our observations accordingly. If this is a probe, and I emphasize that's still an if, but if it is, then we're watching it conduct a mission. It's gathering data, and we have a limited window to gather our own data before it either leaves the solar system or moves too far away to observe clearly. We can't afford to waste time pretending this is definitely just a normal comet when the evidence increasingly suggests it's not." That interview marked a turning point in the public conversation. Here was a respected scientist from MIT, lead author on a peer-reviewed paper, stating plainly that we should take the probe hypothesis seriously. Other scientists began to speak up as well. Not all of them, certainly. The astronomical community remained divided, with a substantial faction insisting that patience and continued natural explanations were the proper scientific approach. But the division itself was significant. The question had moved from the fringe to the mainstream. We were having a serious, scientific debate about whether an object currently moving through our solar system might be a product of alien technology, and then the compositional data took on a new significance. Remember, that weird chemistry, the carbon-rich water pore composition that was so unlike anything we'd seen before. Researchers started asking a different question. If 3I Atlas were artificial, if it were a probe, what would that composition mean? A probe traveling between the stars would face brutal conditions. Cosmic rays, high-energy particles that would degrade most materials over the thousands or millions of years an interstellar journey would take. Impacts with interstellar dust grains at tremendous velocities, each one hitting like a bullet. Extreme cold, just a few degrees above absolute zero, followed by extreme heat as it approached a star. Carbon-based materials, particularly forms of carbon like graphene or carbon nanotubes, have remarkable properties. They're incredibly strong. They're resistant to radiation. They can withstand extreme temperatures. If you were designing a probe's outer hull, a protective shell to survive an interstellar voyage, advanced carbon-based materials would be an excellent choice. The low water content also made sense from an engineering perspective. Water ice would sublimate gradually over a long journey, especially as you approached a star. It would create outgassing that would be difficult to control, potentially throwing off your trajectory. If you wanted a stable, predictable outer coating, something with minimal outgassing until you've deliberately activated it, a carbon-based composition would be far superior to the water-ice mixture of natural comets. The CO and CO2 in the coma, In this interpretation weren't remnants of primordial ices from the object's formation. They were outgassing from a carbon-based hull being heated by the sun. The lack of water wasn't a sign of exotic formation conditions. It was a design choice. This reframing of the compositional data spread through the community in late 2024. And while it remains speculative, it fit the evidence disturbingly well. Every weird data point, every anomaly, made sense if you assumed artificial origin. The strange chemistry, the impossible trajectory, even the object's size, roughly a kilometer across, was consistent with what you might expect for an interstellar probe. Big enough to house significant instrumentation and perhaps power sources, small enough to be feasibly launched and accelerated to interstellar velocities as 2024 turned to 2025. And 3I Atlas continued its journey toward Mars. A growing sense of anticipation and, for some, dread began to build in the astronomical community. The Mars flyby would be the ultimate test. If the object again followed the predicted trajectory, using Mars's gravity to set up the Jupiter encounter, the natural hypothesis would become almost untenable. The probability numbers would drop to something so close to zero that clinging to coincidence would require a kind of willful blindness. But something else was happening too. Something that would transform the debate once more and push it into territory that made even the probe hypothesis seem tame by comparison. The object was changing. The first hints came from photometric data, measurements of how bright the object was over time. Comets naturally vary in brightness as they rotate and as different parts of their surface heat up and create more or less out. But the brightness variations in 3I Atlas weren't following a simple rotation pattern. There were periodicities, yes, but they were complex, with multiple overlapping cycles at different frequencies. Some of the variations seemed to correlate with solar activity. Others had no obvious trigger at all. More detailed observations from Hubble added to the mystery. Hubble can resolve features on 3I Atlas that are a few hundred meters across. Not enough to see fine detail, but enough to get a sense of the object's overall shape and structure. Early images showed what looked like an irregular nucleus, lumpy and asymmetric in the way that cometary nuclei usually are. But images taken in December 2024 showed changes. Features that hadn't been there before, or at least hadn't been visible before, were appearing on the nucleus. The resolution wasn't good enough to say exactly what these features were, but they cast shadows. They had geometric regularity that seemed inconsistent with random ice and rock, and most troubling of all, they were growing. The images were analyzed by planetary scientists, by computer vision experts, by anyone who might offer an alternative interpretation. Could these be ice formations, some kind of unusual sublimation pattern creating regular structures? Could they be imaging artifacts, glitches in the telescope or the processing software? The answer that came back from multiple independent teams was unlikely. The features were real, they were on the object, and they were changing in a way that suggested active processes, not passive erosion or sublimation. By January 2025, some researchers were using a word that sent chills down the spine: deployment. The features looked like something was being deployed from the nucleus, structures extending or unfolding. And that raised the most disturbing question yet. If 3I Atlas was a probe, if it had traveled here from another star, had it been dormant during that long journey? Was it now waking up, activating systems, preparing for its mission in earnest? We'll never know exactly when the decision was made at the highest levels of government. But sometime in January 2025, the object designated 3I Atlas was moved from scientific curiosity to potential security concern. NASA briefed the White House. ESA briefed the European Commission. Every major spacefaring nation with the capability to observe the object began coordinating their efforts, not just as a scientific collaboration, but as a monitoring program. The public narrative remained cautious. Official statements emphasized the uncertainty, the need for more data, the importance of not jumping to conclusions. But behind the scenes, preparations began for scenarios that had previously existed only in science fiction. What do you do if an alien probe is in your solar system? How do you communicate with it? Should you try to communicate with it? What if it's hostile? What if it's just gathering data and has no interest in us at all? What if studying it, really understanding it, could leapfrog our technology forward by centuries? These questions were no longer abstract thought experiments. They were operational concerns being discussed in secure facilities by people with the power to act on them. And through all of this, 3I Atlas continued its journey, indifferent to the chaos it was causing, steadily approaching Mars. The encounter was scheduled for March 2025, just weeks away from the time of this telling. Every telescope that could be spared was being prepared. Deep space communication networks were being oriented toward the object, listening on every frequency for any sign of transmissions. Some scientists were preparing messages to send, just in case it was listening. Though whether humanity should announce itself to an intelligence capable of crossing the stars was a matter of fierce debate that the Mars flyby would tell us more. The data from that encounter would either strengthen the probe hypothesis to the point of near certainty, or just possibly reveal some natural explanation that had eluded everyone so far. But even as the astronomical community prepared for that crucial observation, even as governments quietly made contingency plans and philosophers debated first contact protocols, another discovery was about to emerge from the data. We'd already gathered someone had gone back through all the observations of 3I Atlas from the moment of its discovery, looking for anything that might have been missed in the initial analysis. And in the archival data, in images taken during those first few weeks when the object was still being catalogued and characterized, they found something that had been overlooked. 3I Atlas wasn't alone. There was something else out there, much smaller, barely visible even in the most sensitive images, matching pace with the main object, a companion, a second object. And it had separated from the main body sometime in February, just after discovery, moving on its own trajectory. The revelation that 3I Atlas had released a secondary object, that whatever was happening was even more complex than anyone had realized, would break as news just days before the Mars encounter, transforming the situation yet again. But that's where we'll have to pause this part of the story, because to understand what came next, we need to first understand what happened when 3I Atlas reached the red planet, and what we found when we looked more closely at that impossible trajectory. The evidence was mounting. The questions were multiplying. And somewhere between Mars and Jupiter, something that might not be natural at all was conducting a mission we were only beginning to understand. Whether we were ready for the answers or not, they were coming. The discovery of the secondary object sent shockwaves through an astronomical community, already reeling from one impossible revelation after another. Dr. James Morrison, an astronomer at the European Southern Observatory, had been the one to find it. and only because he'd been obsessive enough to go through every single image ever taken of 3I Atlas, with fresh eyes and new processing techniques. In science, sometimes the most important discoveries are hiding in plain sight, buried in data that everyone assumed had already been thoroughly analyzed. The images from late January 2025 showed it clearly once you knew what to look for. A faint point of light, seemingly insignificant, traveling on a parallel trajectory to the main object. At first, Morrison thought it might be a background star that happened to be in the frame. But as he compared images taken days and weeks apart, he realized the point of light was moving with 3I Atlas, maintaining a consistent distance. Then he went back further into the earliest observations from the discovery in January 2024, and found something that made his hands shake as he adjusted the image contrast. In those first images, there was no secondary object. There was only 3I Atlas itself. But in images from mid-February 2024, barely a month after discovery, the secondary object appeared for the first time. It had separated from the main body. Something had been ejected, released, or deployed from 3I Atlas, and it was now traveling independently through the solar system. Morrison spent 3 days verifying his finding before he reported it. He needed to be absolutely certain this wasn't an imaging artifact, a cosmic ray hit on the detector, a distant asteroid that just happened to be photobombing the images. He calculated the secondary object's orbit independently and found it was definitely associated with 3I Atlas, traveling on a slightly different trajectory, but one that had clearly originated from the same point in space. The separation velocity was low, suggesting a controlled release rather than an explosive ejection. The secondary object was much smaller than the primary, probably no more than a few dozen meters across, maybe even smaller. But it was there, it was real, and it had come from 3I Atlas. When Morrison's report went up the chain of command at ESO and then out to the broader astronomical community, the response was immediate and intense. Every major observatory with archived images of 3I Atlas began searching their data, confirming the finding, refining the measurements of the secondary object's trajectory. Within a week, the confirmation was absolute. 3I Atlas had released something, and that something was now on its own journey through our solar system. The question that dominated every conversation, every email chain, every hastily organized video conference was simple. Why? Why would a comet release a fragment? Why would it do so with such low velocity, as if placing the object carefully rather than explosively shedding material? And where was the secondary object going? Natural comets can fragment. We've seen it happen many times. Comet Shoemaker-Levy 9 broke into more than 20 pieces before it crashed into Jupiter in 1994, giving us one of the most spectacular astronomical shows of the century. But those fragmentations are violent, triggered by tidal forces or internal stresses or impacts. They create pieces that spread out rapidly, each on a slightly different orbit. The secondary object from 3I Atlas hadn't behaved that way at all. The separation was gentle, controlled, deliberate. Trajectory analysis of the secondary object revealed something that was either an astonishing coincidence or more evidence of the intelligent design hypothesis. It was headed for Earth, not on a collision course, nothing that would pose any danger, but on a path that would bring it considerably closer to our planet than the main object. If current projections held, the secondary object would pass within about 2 million kilometers of Earth in late April 2025. Close enough for detailed observation, close enough that some researchers were already proposing we send a spacecraft to intercept it. The timing was impossibly perfect. 3I Atlas itself would be at Mars in mid-March, then continuing on toward Jupiter. But before any of that happened, before we could even process what the main object was doing, we would get a close-up look at whatever it had released. If this was a natural phenomenon, the universe was playing an elaborate joke on us, arranging coincidences with malicious precision. If this was artificial, then whoever or whatever had sent 3I Atlas had planned for us to get a good look at the secondary object. They wanted us to see it, that thought, that implication of intent and design and a plan that accounted for our presence and our capabilities, was more unsettling to many scientists than any other aspect of the entire situation. It suggested that 3I Atlas wasn't just gathering data passively. It knew we were here. It was aware of Earth, aware of humanity, and it was making decisions based on that awareness. Dr. Chen, who had become something of a public face for the trajectory anomaly research, was asked about this in a television interview that aired in early February 2025. The interviewer, a seasoned science journalist who understood the implications, asked bluntly, "Do you think they're trying to make contact?" Chen's answer was careful but chilling. She said, "I think if this is an artificial object, and again we must emphasize that's not proven even though the evidence is pointing that way, but if it is, then releasing a secondary object on a trajectory toward Earth could be interpreted as a message. Not a message in the sense of encoded information, though that's possible too, but a message in the sense of, we see you. We know you're here. Here, look at this. The question is whether we're capable of understanding what they're showing us." As February progressed and the Mars encounter drew closer, the level of observation being directed at 3I Atlas intensified to a degree never before applied to a single object. The Hubble Space Telescope was devoting nearly 40% of its observing time to the object, far more than any single target normally receives. The James Webb Space Telescope was conducting regular spectroscopic observations, tracking any changes in the object's composition or outgassing patterns. Ground-based observatories from Chile to Hawaii to the Canary Islands were imaging it every clear night, building up a comprehensive dataset of its brightness, its shape, its behavior, and everyone was watching those structures on the nucleus. The geometric features that had appeared in December and had been growing ever since. The best images came from Hubble, which had been pushed to the absolute limits of its capabilities. Hubble is old now, launched in 1990, but it's been upgraded and maintained over the decades. And for observing objects in our solar system, it remains one of the best tools we have. In early February, during a period of particularly stable pointing and optimal viewing geometry, Hubble captured a series of images of 3I Atlas that were immediately classified at the highest levels of several governments before being partially released to the scientific community, with certain details redacted. What those images showed was disturbing enough. The nucleus of the object was no longer the irregular, lumpy shape that cometary nuclei usually display. There were flat surfaces now, planes and angles that were geometrically precise. There were structures extending from the nucleus, thin and elongated, that cast sharp shadows on the surface. The structures appeared to be growing from specific points on the nucleus, emerging over the course of weeks in a way that suggested active construction or deployment rather than passive. Geological processes, what the redacted portions of the images showed, we can only speculate about, because the information has not been made public. But researchers who saw the full images, who were brought into secure facilities and shown what Hubble had really captured, emerged shaken. Several refused to discuss what they'd seen, even in vague terms. One, speaking anonymously to a journalist, said only, "It's not a comet. I don't know what it is, but it's not a comet. Nothing natural looks like that." The partial release of the Hubble images in mid-February was enough to cause panic in some quarters and intense fascination in others. The public reaction was divided. A significant portion of the population remained skeptical, viewing the alien probe theory as sensationalism, arguing that there must be natural explanations even if we hadn't found them yet. But a growing number of people, looking at the same data the scientists were looking at, reading the carefully worded papers and the not so carefully worded blog posts and social media threads from astronomers, came to believe that we were witnessing first contact. Not the dramatic Hollywood version with giant ships appearing over cities, but the real version, the slow version, the scientific version, where an object reveals itself gradually and we have to figure out what it means. Religious leaders around the world began weighing in, offering different interpretations of what alien intelligence might mean for various faith traditions. Some saw it as confirmation of divine creation on a cosmic scale, proof that the universe teemed with life and meaning. Others saw it as a challenge to anthropocentric theology, a reminder that humanity might not be the center of the cosmic story. A few, concerning to security services monitoring extremist groups, began preaching that the object was a harbinger of judgment or a demon in disguise. Meanwhile, the scientific community was fragmenting into factions with different views on how to proceed. One group, which we might call the activists, believed that we should make every effort to communicate with 3i, Atlas, or at least demonstrate our intelligence and our awareness of its presence. They proposed broadcasting messages at the object on various radio frequencies, sending tight beam transmissions that included mathematical proofs and representations of Earth and humanity. Some even suggested attempting to send a spacecraft to rendezvous with the secondary object approaching Earth, to get as close a look as possible, and perhaps even attempt physical contact. Another group, the observers, argued for a more cautious approach. Study the object intensively, yes, but don't interfere. Don't announce ourselves if we haven't been noticed already. Gather as much data as possible and try to understand what we're dealing with before we make any moves that can't be taken back. This was the majority position among astronomers, grounded in scientific conservatism and an awareness that we might be dealing with something far beyond our understanding. A third group, smaller but vocal, might be called the fearful. They argued that if 3i Atlas was an alien probe, its intentions were completely unknown and potentially hostile, broadcasting our location, sending spacecraft to intercept it. Even observing it too actively might be dangerous. Better to stay quiet, watch from a distance, and hope it completes whatever mission it's on and leaves. This position was more common among military and intelligence personnel than among scientists, but it had its adherents in the academic community as well. The debate reached the United Nations in late February, when the Secretary General convened an emergency session of the Committee on the Peaceful Uses of Outer Space to discuss 3i Atlas and establish some kind of international protocol for how humanity should respond. The session was contentious, with different nations advocating for different approaches, based on their own strategic interests and philosophical positions. No consensus was reached, but a resolution was passed calling for transparency in observations, sharing of data among all nations, and a prohibition on any unilateral action to make contact or interfere with the object. Without broad international agreement, it was a diplomatic solution to an unprecedented situation, and it satisfied no one, but it at least established that 3I Atlas was a matter for all of humanity, not for any single nation to deal with alone. While diplomats debated and the public argued and scientists scrambled to gather more data, 3I Atlas itself continued serenely on its trajectory, indifferent to the chaos in its wake. It was now close enough to Mars that the Martian orbiters and rovers, originally designed to study the red planet, were being repurposed to observe the approaching interstellar visitor. The Mars reconnaissance satellites, the European Space Agency's Mars Express, NASA's Mars Reconnaissance Orbiter, and several other craft all had instruments that could potentially gather data on 3I Atlas as it passed. The rovers on the surface, Perseverance and Curiosity, had cameras that could image it, though the object would appear as little more than a moving star from the Martian surface. Every asset we had at Mars was being prepared for the encounter, and then, 2 weeks before the scheduled flyby, something happened that transformed the entire situation once more and introduced a new category of anomaly that even the probe hypothesis struggled to explain adequately. The sun erupted. Solar flares and coronal mass ejections are normal features of our star's behavior, especially during periods of high solar activity. The sun goes through an 11-year cycle, and in 2025 we were approaching the maximum of solar cycle 25, when flares and CMEs are most frequent. These events blast enormous quantities of plasma and electromagnetic radiation into space. When directed at Earth, they can disrupt satellites, interfere with communications, and create beautiful auroras. They're dangerous to spacecraft and astronauts, but generally not threatening to life on the ground, protected as we are by Earth's magnetic field and atmosphere. On February 28, 2025, a sunspot region designated AR3615 erupted with an X8.7 class flare, one of the most powerful categories of solar flare. The flare was accompanied by a massive coronal mass ejection, a billion-ton cloud of plasma hurled into space at millions of miles per hour. Solar physicists tracked the CME, calculated its trajectory, and determined that it was headed not toward Earth but off to the side, into a region of space that was mostly empty, except it wasn't empty. 3I Atlas was there. The realization that the CME was on a collision course with the interstellar object came about 18 hours before impact, enough time to alert every observatory that could observe at the relevant wavelengths. Predicting exactly what would happen was difficult. Comets had been hit by CMEs before, and the usual result was increased outgassing, as the blast of radiation and charged particles heated the surface. Sometimes a temporary disruption of the coma and tail, but nothing catastrophic. A comet is too small and too diffuse to be seriously affected by something that spreads out over millions of kilometers of space. But 3I Atlas, if the mounting evidence was correct, might not be a normal comet. If it was artificial, if it had active systems, the CME impact could cause malfunctions, damage, even destruction. Some researchers feared we might lose the object entirely, watching helplessly as our one chance to study alien technology was burned away by our own star's fury. Others wondered if we might learn something profound from how the object responded to the impact. Would its systems fail? Would it try to protect itself? Would we see evidence of shielding, of technology designed to withstand the harsh environment of interstellar space and the hazards of approaching stars? The CME struck 3I Atlas at approximately 14:30 UTC. On March 1st, 2025, every telescope that could observe the object was watching. Satellites designed to study the Sun were tracking the CME itself. The data that came back in the hours and days following the impact would provide some of the most compelling evidence yet that 3I Atlas was something unprecedented. The first indication that something unusual was happening came from the sudden brightening. As the CME engulfed the object, observers expected to see a gradual increase in brightness over minutes or hours as the surface heated and outgassing increased. Instead, the brightening was almost instantaneous and far more intense than any model predicted. Within seconds of the CME impact, 3I Atlas went from being a faint smudge, visible only in sensitive telescopes, to being bright enough to see with good binoculars, almost visible to the naked eye. It brightened by a factor of 40, an increase that shattered all expectations. More striking than the magnitude of the brightening was its character. The increased light wasn't coming from diffuse outgassing from a general heating of the surface. It was coming from specific points on the nucleus, the same locations where those geometric structures had been growing. The brightness was focused, concentrated, as if the object was channeling the energy from the CME into particular systems rather than absorbing it across the entire surface. Spectroscopic observations during and after the impact revealed something even more bizarre. The spectrum of light from 3I Atlas changed dramatically. Before the impact, the spectrum showed the typical emission lines of a comet: carbon dioxide, carbon monoxide, some simple organic compounds being boiled off the surface. After the impact, new emission lines appeared, wavelengths of light that didn't correspond to any simple molecular output. Some of the lines matched highly ionized metals, elements that should only be present in trace amounts in a comet, and certainly shouldn't be glowing brightly enough to dominate the spectrum. Dr. Rebecca Santos, a spectroscopist at the California Institute of Technology, was monitoring the object during the CME impact and captured what she later called the most anomalous spectrum I've ever seen from any object, anywhere. In interviews, she described her reaction. "I thought our instrument had broken. The spectrum made no sense for a comet. It looked more like what you'd see from a planetary nebula or some kind of industrial plasma. But we checked every calibration, ran every diagnostic, and the data was good. The light really was coming from 3I Atlas, and it really did have that impossible spectrum. Either this object contains elements and compounds that have no business being there in those quantities, or something on that object is actively producing emissions in response to the CME. Something technological." The brightening lasted for approximately 6 hours, then gradually faded over the course of 3 days, returning the object to roughly its pre-impact brightness. But it didn't return to exactly the same state. The photometric data, the measurements of brightness variations over time, showed new periodicities, new patterns that hadn't been there before. The object appeared to be rotating differently, or perhaps the distribution of reflective surfaces on its surface had changed. Something about 3I Atlas was different after the CME impact. The interpretation of these events split the scientific community even more deeply than before. Those favoring natural explanations pointed out that we didn't fully understand cometary outbursts. That unusual volatile compositions could potentially explain the spectrum if the object had formed in an exotic enough environment, that the brightening could have been triggered by the CME cracking open fresh ice deposits that then explosively vented. It was all very unlikely, yes, but unlikely wasn't impossible. Those favoring the artificial hypothesis saw the CME response as smoking gun evidence. A natural comet doesn't channel energy to specific locations. It doesn't produce spectra that look like industrial plasma. It doesn't survive a direct hit from Acme unscathed, and then emerge with altered rotation characteristics. The response of 3I, Atlas looked exactly like what you'd expect from an engineered system reacting to an energy input, absorption, conversion, distribution to where it's needed, and then a return to normal operations with some systems altered by the experience. The most disturbing interpretation, one that circulated in private conversations and classified briefings but rarely appeared in public statements, was that 3I Atlas had used the CME, that the object had somehow absorbed the energy from the coronal mass ejection and converted it into power for its own systems. That the brightening wasn't damage or uncontrolled venting, but the visible signature of energy collection and storage. If true, it meant the object had technology that could harvest stellar plasma and electromagnetic radiation on a massive scale. Technology that was far beyond anything in our current capabilities or even our theoretical understanding. It also meant the object might not need conventional fuel or power sources. It could potentially operate indefinitely in any solar system, drawing energy from the star itself, from solar wind and flares and the constant output of radiation. An interstellar probe powered by the very stars it visited would have virtually unlimited operational lifetime. It could study a system for years, decades, even centuries if needed. These speculations were fueled by another observation made in the days following the CME impact. The geometric structures on the nucleus were larger now. Whatever was being built or deployed or unfolded from the object's surface, the process had accelerated. Analysis of the higher resolution images suggested the structures had grown by 15 to 20% in just the 3 days following the impact. If that growth rate continued, if it was powered by energy harvested from the sea, within weeks the structures might be large enough to resolve their actual shape and function. Dr. Chen, in another interview that went viral, was asked whether she thought the CME impact had damaged the object or powered it up. Her answer was stark. Everything we're seeing suggests that object is more active now than it was before the impact. Whatever those structures are, they're growing faster. The rotation state has changed, which might mean something has deployed or reconfigured. The spectrum shows emissions that shouldn't be there. To me, and I acknowledge this is interpretation rather than definitive proof, but to me, it looks like we just watched that thing wake up. And that's either the most exciting or the most terrifying thing I've ever witnessed in my career. Possibly both. The Mars flyby was now just 2 weeks away, and the level of anticipation had reached a fever pitch. Every nation with spacecraft at Mars was coordinating their observations, establishing exact timing and targeting for their instruments. The orbiters would track 3I Atlas as it approached, measuring its trajectory with extreme precision to see if it again followed the predicted path. They would image it with every camera available, capturing the geometric structures in as much detail as possible. They would measure its magnetic field, its plasma environment, any radiation it might be emitting. Some of the instruments would be looking for something specific, evidence of active propulsion, because there was another puzzle embedded in all of this. another anomaly that had been bothering a subset of researchers who specialized in spacecraft dynamics and orbital mechanics. The trajectory of 3I Atlas was so precise, its gravity-assisted flyby so perfectly calculated, that it suggested not just navigation but active course correction. The non-gravitational forces from outgassing could only do so much. They could nudge an object, push it slightly off course. But controlling a trajectory to the precision that 3I Atlas was displaying would require more than that. It would require thrust, deliberate acceleration in specific directions at specific times, but we hadn't seen any evidence of thrust. No rocket plumes, no jets of material that would indicate propulsion. The object appeared to be moving under the influence of gravity and subtle non-gravitational forces. Nothing more, unless the propulsion system was something we didn't recognize. Something that didn't produce obvious signatures. Electric propulsion, like the ion drives used on some of our deep space probes, produces very little visible evidence of operation, but can provide small, sustained thrust over long periods. That was possible. Or perhaps the propulsion was even more exotic, based on principles we didn't understand. The point was, if 3I Atlas was actively navigating, it had to be using some form of propulsion, and we hadn't identified it yet. The Mars instruments were specifically tasked with looking for any signs of thrust, any particles or radiation or magnetic field changes that might reveal how the object was controlling its trajectory. If they found something, if they identified a propulsion mechanism, it would be the most direct evidence yet of artificy, IALITY. As the Mars encounter approached, another issue was moving up the chain of command at NASA and ESA and becoming a matter of serious discussion. The question of mass. A comet's mass determines how it responds to gravitational forces and to its own outgassing by analyzing an object's trajectory, especially how it responds to the gravitational pulls of planets it passes. You can estimate its mass. Multiple teams had been running these calculations for 3I Atlas, and the numbers were problematic to follow the trajectory it was following. With the non-gravitational accelerations it was displaying, 3I Atlas needed to have a certain minimum mass to light, and the outgassing forces would push it off course. Too heavy, and the gravitational influences of the planets wouldn't bend its path the way they were observed to. The calculations, run by different groups using different methods, all converged on a minimum mass of roughly 30 to 35 billion metric tons. That might sound like a lot, but for an object a kilometer across, it's actually reasonable if the object is made of typical cometary material, a mix of ice and rock with a lot of empty space. The density would work out to maybe half that of water ice, which is what you'd expect for a fluffy, porous comet. But there was a problem. When you calculated the mass based on how much material the object was ejecting, based on the brightness of the coma and the rate of sublimation, you got a different number. The object wasn't outgassing enough material to have that much mass. The amount of volatiles it was releasing suggested something much smaller, much less massive, maybe a tenth the mass that the trajectory analysis required. There were only a few ways to reconcile this discrepancy. One possibility was that the object wasn't outgassing uniformly, that most of its surface was inactive and only small regions were releasing material. That would mean it had much more mass than the outgassing suggested, locked up in a dense core or in materials that weren't sublimating. Possible, but it would make 3I Atlas very different from typical comets, which outgas more or less uniformly across their dent facing. surfaces. Another possibility was that our calculations of the mass required for the observed trajectory were wrong. Maybe there were additional forces at play that we weren't accounting for. Something that would allow a less massive object to follow the path we were observing. But the physics was pretty straightforward, and multiple independent groups were getting the same answer. The math didn't leave much room for error. The third possibility was one that most researchers didn't want to say out loud. The object was denser than it should be, far denser. If you packed a kilometer-sized object with 35 billion tons of mass in a form that didn't outgas much, didn't release significant volatiles, even when heated by the sun, you'd end up with a density that was absurdly high for any natural cometary material. You'd be approaching the density of solid rock or even metal. And if it was that dense, that massive, it would have gravitational effects we should be able to measure. Small, yes, but detectable. One researcher, in a moment of hyperbole that was quickly walked back but that captured the essence of the problem, calculated that to have the mass the trajectory suggested while producing the minimal outgassing observed, 3I Atlas would need to be denser than neutron star material. That was obvious nonsense. Physics doesn't work that way, but the comment highlighted the genuine puzzle. The mass estimates from different methods didn't match, and the discrepancy was large enough that it couldn't be ignored. The explanation that was emerging, cautiously, in technical papers and conference presentations, was that 3I Atlas was disguising its true mass somehow, that it was deliberately producing just enough outgassing to look comet-like, but not so much that it lost significant material, that the coma and tail were, in essence, camouflage. And if you were trying to disguise a spacecraft as a comet, that's exactly what you'd do. Release just enough gas and dust, create the appearance of a natural object while keeping your actual mass and composition hidden. This masking hypothesis was controversial because it required attributing intent and sophisticated technology to the object. You couldn't accidentally disguise your mass. It would require active control of outgassing, selective release of materials, possibly even artificial generation of the coma through some kind of mechanism that mimicked natural sublimation. But it explained the observations in a way that natural processes struggled to. The Mars encounter would provide another data point for the mass calculations. By measuring exactly how Mars's gravity affected 3I Atlas, by tracking the tiny wobbles in Martian satellite orbits as the object passed, we could get an independent estimate of the object's mass based purely on gravitational interactions. If that number matched the 35 billion tons from the trajectory analysis, it would confirm the object was as massive as it seemed. If it didn't match, if the gravitational measurements suggested something much less massive, we'd know the trajectory was being controlled by forces other than natural forces that didn't add up in the conventional equations. Either way, the Mars encounter promised answers, or at least better questions. On March 15th, at approximately 9:17 UTC, 3I Atlas made its closest approach to Mars, passing within 8.3 million kilometers of the red planet. Every instrument we had at Mars was watching. Every telescope on Earth that could observe through the daylight or had a clear line of sight was recording. Communication networks listened on every frequency, searching for any transmissions. Any signals that might indicate the object was more than it appeared. The flyby took hours to complete as the object approached, reached periapsis, and then receded. The data streamed back to Earth at light speed, arriving at various ground stations around the world in near real. Initial analysis began immediately, thousands of researchers working in parallel to process images. spectra, trajectory measurements, magnetic field readings, everything we'd gathered. The preliminary results, released in a terse NASA statement 6 hours after closest approach, confirmed what everyone both hoped and feared. Trajectory of interstellar object 3I Atlas, consistent with pre-encounter predictions. Object is now on a path toward Jupiter as calculated. It had done it again. The precision navigation, the impossible alignment, the trajectory that would make mission planners jealous. 3 planetary flybys in a row, each one mathematically predicted by models that assumed intelligent navigation, each one confirmed by observation. The probability calculations from the original 20-scientist paper, already astronomical, could now be updated to even more extreme values. Random chance had just become statistically impossible. If this was natural, if there was no guidance system, no active control, then the universe had violated its own rules to produce this result. But the trajectory confirmation was just the beginning of what the Mars encounter revealed. The real findings, the data that would take weeks to fully analyze and longer to fully understand, showed something that went far beyond mere navigation. The images from the Mars Reconnaissance Orbiter's higher ISK camera, designed to photograph the Martian surface at resolutions high enough to see individual rocks, had been pointed at 3I Atlas during the closest approach. The distance was still millions of kilometers, far greater than hierarchy was designed to observe, but the camera's exceptional optics still managed to capture details of the object that had never been seen before when those images were processed, enhanced and examined by teams of planetary scientists and image analysts. The conclusion was inescapable. The geometric structures on the nucleus weren't geological features. They weren't ice formations or sublimation patterns or any kind of natural phenomenon. They were constructed. They had joints, segments, regular patterns that repeated with precision. They looked, for lack of a better word, technological. They looked built, and they were still growing. Comparing images taken at the beginning of the encounter to images taken at the end, hours later, showed measurable differences. The structures were extending, unfolding, assembling themselves in real time as we watched. Whatever process had been initiated, possibly triggered by the CME impact 2 weeks earlier, it was continuing, accelerating even. The implications were staggering. We weren't just observing an alien probe, if that's what this was. We were watching it transform, activate, deploy. It was doing something, building something, preparing for something, and we had no idea what. We could see it happening. We could measure it and photograph it and analyze the light it reflected, but we couldn't understand it. The technology gap, the difference between what we could do and what 3I Atlas was apparently capable of, was too vast as the data from the Mars encounter continued to be analyzed. As researchers struggled to make sense of observations that challenged everything they thought. They knew about comets and spacecraft and what was possible. The secondary object, the smaller companion that had been released months earlier, continued its own journey toward Earth in just 6 weeks. It would make its closest approach to our planet, close enough for us to study it in detail. Close enough that some were proposing we try to make physical contact. The question of what we should do, how we should respond to this unprecedented situation, was about to become very urgent indeed. Because if 3I Atlas was a probe, if it was truly artificial and truly here for some purpose, then the secondary object approaching Earth might be a message, an invitation, a warning. or something we couldn't even imagine. And humanity was about to find out which dot in the 6 weeks between the Mars encounter and the projected closest approach of the secondary object to Earth. The world transformed in ways both subtle and profound. It wasn't a sudden change, not the kind of dramatic before and after moment that marks wars or natural disasters. Instead, it was a gradual shift in perspective, a creeping realization that spread through human consciousness like dawn light moving across a planet's surface. We were not alone. We had probably never been alone. And something from out there, from the vast darkness between stars, was here in our solar system, possibly trying to tell us something. The secondary object, which had been given the designation 3I Atlas B by the International Astronomical Union, became the focus of an observational campaign unprecedented in the history of astronomy. Every major telescope that could be spared from other observations was scheduled for at least some time looking at this tiny speck of reflected light crossing our solar system. The object was small, perhaps only 20 to 30 meters across, based on its brightness and estimated reflectivity. But it was approaching Earth on a trajectory that seemed almost too perfect to be coincidental. Dr. Helena Vasquez, an orbital dynamics specialist at the Jet Propulsion Laboratory, was leading one of several teams tracking the secondary object's path with extreme precision. By late March, as more and more positional measurements accumulated, she had refined the closest approach distance to within a few thousand kilometers of uncertainty. The object would pass approximately 1.8 million kilometers from Earth on April 27th, about 4.5 times the distance to the Moon, close enough for excellent observation with ground-based telescopes, close enough that radar installations like the Arecibo replacement, facility in Puerto Rico and the Goldstone Deep Space Communications Complex in California could potentially bounce signals off it and measure its shape and rotation directly. But what made Vasquez's blood run cold, what she verified 3 times before reporting to her superiors, was the geometry of the approach. The secondary object wasn't just passing near Earth. It was approaching along a path that would bring it into what mission planners call a favorable communication geometry. Its trajectory, velocity, and timing meant that for approximately 48 hours around closest approach, the object would be moving slowly relative to Earth, at an angle that would allow continuous observation from ground stations, and at a distance where radio communication would have a round-trip light time of only about 12 seconds if you were designing a mission to make contact with whoever lived on the 3rd planet of this solar system. If you wanted to position a communications relay or observation post where it could interact with Earth efficiently, you would put it almost exactly where 3I Atlas B was going to be on April 27th. The trajectory wasn't just close. It was optimal. It was deliberate. Vasquez's report triggered a cascade of meetings at the highest levels of government and international space agencies. The question was no longer theoretical. What do we do if we have the chance to communicate with an alien probe? The question was now immediate and practical. What do we do in the next 4 weeks to prepare for possible first contact? The debates were intense and sometimes bitter, cutting across national boundaries, scientific disciplines, and philosophical worldviews. At one extreme were those who argued for aggressive attempts at communication, broadcasting messages at the object on every frequency we could manage, using powerful transmitters to send everything from prime numbers to images of Earth, to samples of human music and art. If this was our chance to announce ourselves to a broader galactic community, to demonstrate our intelligence and our culture. We couldn't waste it with timidity. At the other extreme were those who counseled complete silence and minimal observation. We didn't know what the object was or what its creators intended, broadcasting our presence, revealing the details of our civilization, our technology level, our location beyond what was already obvious, could be catastrophically dangerous. Perhaps the object was simply passing through and hadn't noticed us. Perhaps drawing attention to ourselves was the worst possible choice. The dark forest theory of cosmic sociology, popularized by science fiction but taken seriously by some researchers, suggested that advertising your presence to unknown civilizations was a form of suicide. Better to stay quiet, watch from the shadows, and hope we were beneath the notice of whatever sent 3I Atlas, the middle ground. Where most scientists and policymakers eventually landed was cautious engagement. We would observe the secondary object intensively, using every instrument we had. We would listen for any transmissions on all frequencies. We would send a carefully crafted message, something that demonstrated our mathematical and scientific knowledge without revealing anything that could be used against us. And we would send it only after international agreement on its content. And we would prepare, as best we could, for whatever we might discover, but preparing for first contact when you don't know. What you're making contact with is a challenge that pushes the boundaries of human imagination and capability. A hastily assembled committee of scientists, linguists, philosophers, and security experts was tasked with drafting the message that would be transmitted to 3I Atlas B. The constraints were daunting. The message needed to be understandable to an intelligence that might think in completely alien ways, that might not have concepts like language or mathematics in any form we'd recognize. It needed to avoid revealing vulnerabilities while still demonstrating that we were worth talking to. And it needed to fit in a transmission format that could be sent without existing equipment. The committee spent 3 weeks in almost continuous deliberation before producing a final message package. It began with a series of prime numbers, the universal language of mathematics that any technological civilization should recognize. Then came representations of the hydrogen atom, the most common element in the universe, showing the hyperfine transition that produces the 21 centimeter wavelength used in radio astronomy. This established a common reference for physical constants and units of measurement. From there, the message built up in complexity, mathematical constants like pi and e, geometric diagrams, a representation of the solar system with Earth's position marked, a crude map of Earth's surface showing continents and oceans, and finally, a simple binary image of a human figure with a hand raised in greeting. The entire message could be transmitted in under 10 minutes and repeated continuously during the 40-8-hour window when 3I Atlas B was in optimal position. Some committee members had pushed for including more, for sending music or literature or detailed information about human civilization. Others had argued for sending less or nothing at all. In the end, the message that was approved was a compromise, carefully designed to say we are here, we are intelligent. We would like to communicate without saying much more than that. While the message was being prepared, another effort was underway, more ambitious and more controversial. A small group at NASA's Advanced Concepts Division, working with engineers from SpaceX, Blue Origin, and several other aerospace companies, was studying whether it was possible to launch a spacecraft to rendezvous with 3I Atlas B during its Earth approach. The timeline was brutal. For weeks to design, build, and launch a probe that could match trajectories with an object moving at several kilometers per second relative to Earth. Normally, a mission of this complexity would take years of planning and months of preparation at minimum. But these weren't normal circumstances, and the potential scientific return from getting a close-up look at the secondary object, possibly even landing on it or collecting a sample, was beyond calculation. The conclusion, delivered to NASA's administrator with a mixture of excitement and trepidation, was that it was just barely possible. Using a heavy lift launcher that was already being prepared for a different mission, flying a trajectory that would stress every component to its limits, and accepting risks that would never be approved for a normal mission, they could get a small spacecraft to 3I Atlas B. The payload capacity would be minimal, maybe 100 kilograms, including fuel for final approach. But that was enough for cameras, spectrometers, maybe a simple sampling arm. The decision of whether to attempt the mission went all the way to the President of the United States. In consultation with international partners, the arguments for proceeding were compelling. This might be our only chance to examine an artifact of alien technology up close, to gather data that could advance human knowledge by centuries. The arguments against were equally strong. The mission would be dangerous, expensive, and might be seen as provocative by whatever intelligence had sent the objects. There was also the uncomfortable possibility of failure. If we sent a spacecraft and it malfunctioned, or if the secondary object took evasive action or destroyed the approaching probe, it would be a very public humiliation. On April 3rd, the decision was announced. Humanity would attempt to make contact. The mission, named Envoy 1, would launch no later than April 15th, giving it enough time to reach the intercept point. The spacecraft would approach 3I Atlas B cautiously, observing from a safe distance first, then moving closer if the object showed no signs of hostility or active maneuvering. The mission would be controlled jointly by NASA and ESA, with participation from JAXA, Roscosmos, and other space agencies. It would be a mission for all of Earth, not just one nation. The announcement was met with reactions ranging from jubilation to horror. Public opinion polls showed a sharp divide, with slight majority supporting the mission, but a large minority convinced it was reckless or dangerous. Religious leaders offered prayers and blessings. Protest groups organized outside NASA facilities, and through it all, aerospace engineers worked around the clock to make the impossible happen on an impossible timeline, while Envoy 1 was being frantically assembled. 3I Atlas itself, the primary object, continued its journey toward Jupiter, and the observations of its ongoing transformation became more detailed and more unsettling with each passing day. The structures on the nucleus were no longer small or ambiguous. By early April, they were large enough and distinct enough that even amateur astronomers with good equipment could see them as bumps or protrusions on the object's profile. Professional observations from Hubble and the larger ground-based telescopes revealed them in stunning detail. Geometrically precise constructions extending from the nucleus like the petals of some vast mechanical flower opening in slow motion. Dr. Michael Torres, an aerospace engineer with decades of experience in spacecraft design, was brought in to consult on what the structures might be. After reviewing the images and the measurements of how they'd grown over time, he produced a report that circulated widely in classified channels before being partially leaked to the press. His conclusion was direct and unambiguous. The structures were solar panels, not exactly like human solar panels, of course. The geometry was different, the materials were unknown, and the scale was vastly larger than anything we'd deployed. But the function appeared identical. Large, flat surfaces with geometric regularity, oriented to maximize exposure to sunlight, extending from a central body that presumably housed the systems they were powering. Torres estimated that when fully deployed, the panels would have a collection area of several square kilometers, capable of generating gigawatts of power if they were even moderately efficient. The implication was, Clear 3I Atlas was powering up. The CME impact in early March had triggered something, and that something was the deployment of massive energy collection systems. The probe, if that's what it was preparing for some energy-intensive operation. And given that it was heading toward Jupiter, given that its trajectory seemed designed to place it in orbit around the giant planet, or at least to conduct a very close flyby, whatever operation it was preparing for was probably going to happen there. This realization sparked another round of frantic observation planning. Every space agency with assets in the outer solar system, which mainly meant NASA with its Juno orbiter at Jupiter and the New Horizons spacecraft now far beyond Pluto but potentially still useful as a distant observation post, began reprogramming their missions. Juno, in its elliptical orbit around Jupiter, was particularly well. It would be able to observe 3I Atlas as the object approached the giant planet, potentially getting closer views than any telescope on Earth could achieve. The Juno team published a revised observation plan that showed the spacecraft could potentially pass within a few 100,000 kilometers of 3I Atlas during the encounter, close enough for its instruments to measure magnetic fields, radiation, and capture high-resolution images. It would be risky, using fuel reserves that were meant to keep the spacecraft operational for its primary mission. But the scientific value of observing an interstellar object, possibly an alien probe, at close range was too great to pass up. As April progressed and the 27th approached, the level of public attention reached fever pitch. The Envoy 1 spacecraft launched successfully on April 14th. A flawless liftoff, watched by hundreds of millions of people around the world. The spacecraft was small, simple, built with off-the-shelf components where possible and hasty custom engineering where necessary. But it was functional and it was on its way. The trajectory would take 13 days, with the final approach beginning on April 26th. Meanwhile, the message that had been so carefully crafted was ready to transmit. The Arecibo replacement facility, along with several other large radio telescopes around the world, was prepared to begin broadcasting toward 3I Atlas B on April 25th, giving the object time to receive and potentially respond before the Envoy 1 encounter. The transmission would be powerful, beamed directly at the object's predicted position with enough strength that even a small receiver should be able to detect it across the million-plus kilometers of space between us. But even as humanity prepared to announce itself, to reach out across the void with a message of greeting and curiosity, other observations were revealing details about 3I Atlas B that suggested the object might already know exactly where we were and what we were. The first hint came from photometric measurements, tracking how the object's brightness changed over time. Small objects in space usually tumble, rotating chaotically due to outgassing forces or the random momentum they inherited from formation or fragmentation. This tumbling shows up as periodic brightness variations as different surfaces catch the sunlight. 3I Atlas B showed brightness variations, but they weren't random tumbles. The object was rotating in a controlled manner, one face always pointed roughly toward Earth. Gravitational gradient stabilization could explain this for natural satellites orbiting a planet, where tidal forces lock one face toward the primary body. But 3I Atlas b wasn't in orbit around Earth. It was in a hyperbolic trajectory, just passing by. There was no natural mechanism that would keep it pointed at us. The orientation was deliberate. The object was tracking Earth. The second hint came from spectroscopic observations. The reflected light from 3I Atlas b showed absorption, features that didn't match any common minerals or ices. Dr. Santos at Caltech, who had analyzed the bizarre spectrum from 3I Atlas during the CME impact, examined the secondary object's spectrum and found similar anomalies. The spectral signature suggested materials with complex molecular structures, possibly organics, possibly something more exotic. But there were also sharp absorption lines that looked almost like they came from manufactured materials, polymers or composites designed for specific optical properties. One researcher, speaking anonymously because the speculation was too wild to attach their name to publicly, suggested the spectrum looked consistent with what you might expect from a spacecraft hull designed to be low absorbing rather than reflecting most wavelengths to avoid detection. If true, it meant we were only seeing the object because it was allowing us to see it, because it was reflecting just enough light to be tracked. The thought that 3I Atlas b might be using stealth technology, that there might be other objects out there we couldn't see, sent chills through the intelligence and defense communities. On April 25th, at precisely 14 o'clock UTC, the transmission began. Radio waves carrying humanity's greeting. Our announcement of presence and intelligence spread outward from Earth at the speed of light, crossing the diminishing distance to 3I Atlas b in about 6 seconds. The message repeated continuously, a loop of mathematics and science and a simple image of a human form reaching out. For the first 12 hours, there was no response. The radio telescopes listened on every frequency they could monitor, searching for any reply, any acknowledgement. There was nothing but the background hiss of the cosmos, the random crackling of distant stars and galaxies, and the faint echo of the Big Bang itself still reverberating through space. Then, at 2:37 UTC on April 26th, the Very Large Array in New Mexico detected something. A signal, faint, but definitely artificial, coming from the direction of 3I Atlas b. It wasn't on the frequency we'd been broadcasting on. It was higher, in a part of the spectrum we'd been listening to, but not transmitting on. And it wasn't random noise or natural emission. It was structured, patterned, modulated in a way that clearly indicated information content. The detection triggered emergency protocols that had been established weeks earlier. The signal was recorded, verified by multiple stations, and analyzed by teams working in secure facilities. The structure of the signal was strange, not like any communication protocol humans had developed, but certain elements were familiar. There were repeating sequences that might be headers or timing markers. There were variations in amplitude and frequency that encoded information, and buried in the complexity, in a pattern that took hours to extract, was something that made the analysis teams stop in their tracks. The signal contained prime numbers, the same prime number sequence we had sent in our message, played back to us with perfect fidelity. It was an echo, an acknowledgement, proof that our transmission had been received and understood. 3I Atlas b was talking back. The news broke globally within hours, despite attempts to control the information flow. Someone in the analysis chain leaked it, or maybe it was inevitable given how many people were involved, how many institutions were monitoring the signals. By dawn on April 26th, the world knew we had made contact. The alien probe, or whatever it was, had responded to our message. The reaction was complex and overwhelming. Stock markets crashed and recovered in wild swings as investors tried to process what this meant for the future. Religious services around the world filled with people seeking comfort or guidance or celebration. Scientists cautiously celebrated, knowing that one exchange of prime numbers didn't constitute full communication, but recognizing it as an epical moment nonetheless. And governments scrambled to coordinate their response, to figure out what to say next. Whether to say anything next, the decision was made to continue transmitting the original message, but also to add to it, to attempt to build a more complex dialogue. Mathematicians and cryptographers worked through the night to design follow-up messages that built on the prime number foundation, adding simple arithmetic, then algebra, then attempting to establish a symbolic language that could convey more abstract concepts. But even as Earth tried to figure out how to talk to 3I Atlas B, the object itself was being studied in unprecedented detail as it drew closer. Radar observations from Goldstone and other facilities were bouncing signals off it and measuring the return, building up a three-dimensional model of its shape. What those radar images revealed was profoundly strange. The object wasn't irregular and lumpy like an asteroid or cometary fragment. It was smooth, regular, almost spherical, but not quite. There were features on the surface, geometric patterns that showed up as bright returns in the radar data, suggesting metal or something with similar reflective properties. And there was a peculiarity in the rotation. The object was spinning, but not around its center of mass. It was rotating around a point that was offset, suggesting either a very unusual mass distribution or, more likely, that the object was actively controlling its rotation with internal mechanisms. By the evening of April 26th, as 3I Atlas B approached within 2 million kilometers of Earth, as the Envoy 1 spacecraft maneuvered for its final approach, another signal was detected. This one was different from the first response. It was stronger, more complex, and it contained more than just mathematics. The signal, when analyzed, appeared to include imagery. The encoding was unfamiliar, but information theorists working on the problem recognized it as having the statistical properties of compressed visual data. After hours of work, trying different decoding schemes and display formats, a grainy, low-resolution image emerged from the data. It showed Earth, unmistakably, unambiguously Earth, a blue marble with familiar countenance and swirls of white clouds. The perspective was from space, similar to the famous blue marble photograph taken by Apollo 17. But the cloud patterns were current, matching satellite imagery from just days earlier. The object had photographed Earth. It had studied us, mapped us, and now it was sending the image back, as if to say, yes, we see you, we know you're there. We've been watching. The implications cascaded through the analysis teams. This wasn't a passive object stumbling through our solar system. It had active sensors, probably cameras or imaging systems of some kind, and it had been observing Earth closely enough to capture detailed images. How long had it been watching? Since it entered the solar system? Longer. The object could have been observing us with distant sensors for months, learning about us, preparing. Preparing for what? That question hung heavy over all the deliberations, all the press conferences, all the public and private discussions about what was happening. If 3I, Atlas, and its secondary object were probes sent by some alien civilization, what was their mission? Scientific exploration, like our own Voyager or Pioneer spacecraft that carried messages to any aliens they might encounter. That was the optimistic interpretation, the one that allowed us to sleep at night. But there were darker possibilities. Reconnaissance before invasion, evaluation for resource extraction, or purposes so alien we couldn't even imagine them, carried out by beings whose motives were utterly incomprehensible. Dr. Chen, in yet another interview that tried to balance scientific caution with public anxiety, was asked directly if we should be afraid. Her answer was careful. Fear is a natural response to the unknown, but it's not necessarily useful. What we're witnessing is unprecedented in human history, but so far, the object has done nothing hostile. It's following a trajectory, it's deploying structures, it's responding to our communications. These all seem like the actions of a scientific mission, something exploring and gathering data, not something preparing for conflict. But I emphasize the word seem. We're interpreting alien actions through human frameworks, and that's dangerous. We might be completely misunderstanding what we're seeing. So caution, yes. Vigilance, absolutely. But paralyzing fear, that doesn't help us learn, and learning is our best defense right now. As dawn broke on April 27th in different time zones around the world, billions of people looked up at the sky, knowing that somewhere out there, invisible to the naked eye, but tracked by countless instruments, an object from another star was passing its closest point to Earth, and a fragile human spacecraft, carrying the hopes and fears of an entire species, was approaching it. The Envoy 1 encounter was scheduled to begin at 11 o'clock UTC. The spacecraft had performed its final trajectory correction, burns, and was now on a coast phase. Instruments active, cameras recording. The plan was to approach to within 10,000 kilometers, about the altitude of a GPS satellite. Close enough for detailed observation, but far enough to be safe. If the object took defensive action or proved to be hazardous in some way, mission control at JPL was crowded with engineers, scientists, and observers from space agencies around the world. The room was silent except for the periodic call-outs of telemetry and status checks. Everyone knew that at the speed Envoy 1 was traveling, the window for observation would be brief, just a few hours from first approach to final separation. Every second counted, every instrument reading was precious. At 11:14 UTC, Envoy 1's optical camera acquired 3I, Atlas B, a bright point against the starfield, exactly where it was predicted to be. The spacecraft's guidance system locked onto the target and began making minute adjustments to optimize the flyby trajectory. As the range decreased, the point of light resolved into a disk, then into an object with visible features, the first images, transmitted back to Earth with agonizing slowness given the limited bandwidth, showed something that was unmistakably artificial. The object was spherical, about 25 meters in diameter, with a surface that appeared metallic or ceramic, smooth and reflective. There were markings on the surface, panels or sections that suggested modularity, components fitted together. And there were what looked like sensor ports or windows, dark circular features that might house cameras or other instruments. But the most striking feature, the one that dominated the images and the subsequent analysis, was a structure extending from one hemisphere of the sphere. It looked like an antenna, a long thin boom made of segments that had clearly unfolded or deployed from the main body. At the tip of the antenna was a dish-like structure, and it was pointed directly at Envoy-1. The probe was watching our spacecraft, tracking it with its own sensors, just as we were watching it. The two machines, one from Earth and one from somewhere beyond our solar system, were regarding each other across a few thousand kilometers of space, each trying to understand what the other was. Envoy-1 cycled through its instrument suite, gathering as much data as possible in the limited time available. Cameras captured images in multiple wavelengths. A spectrometer analyzed the reflected sunlight to determine the composition of the sphere's surface. A magnetometer measured any magnetic fields the object might be generating. A particle detector searched for radiation or exotic emissions. The data, when it was fully analyzed over the following days, would reveal tantalizing details. The sphere's surface appeared to be made of a metallic alloy with properties unlike any terrestrial material, possibly involving elements heavier than anything commonly found on Earth. The object was generating a weak, but measurable magnetic field, suggesting active electrical systems inside, and there was a faint but definite emission of particles, a stream of charged ions being ejected from one region of the sphere at low velocity, possibly a form of attitude control, or even propulsion. But the most important finding came from the radio receiver on Envoy-1, which had been listening throughout the approach for any transmissions from the object. At 11:47 UTC, at the point of closest approach, 3I Atlas B transmitted a burst of data directly at the spacecraft. The transmission lasted only a few seconds, but it was dense with information, thousands of bits packed into multiple carrier frequencies. The spacecraft recorded everything and relayed it back to Earth, where teams were waiting to begin the analysis. It took 2 days to decode the transmission, to figure out the structure and extract the contents. What they found was a series of images, far more detailed and clear than the one that had been transmitted earlier showing Earth. These images showed the solar system from various perspectives, tracking the journey of both 3I Atlas and 3I Atlas B from the outer reaches inward. They showed the Sun, the planets, their orbits rendered with precision. They showed Earth in detail, continents and oceans and ice caps. And overlaid on the image were markers, symbols that might indicate features of interest or importance. But there were also images of something else, something that took longer to understand. They appeared to be star maps, charts showing constellations as they would appear from different locations in the galaxy. And one of those maps had a marker, a highlighted star, possibly indicating the origin point of 3I Atlas. If the map could be properly interpreted, if the constellations could be matched to our own astronomical catalogues, we might be able to determine where the probe had come from, which star system had sent it. Astronomers worked frantically to match the patterns, to identify the stars shown in the transmitted images. The difficulty was that the perspective was alien. The stars shone as they would appear from somewhere else in the galaxy, and matching them to our familiar constellations required sophisticated software and a lot of trial and error. On April 30th, a team at the Harvard-Smithsonian Center for Astrophysics announced they had a match. The star map, when properly oriented and compared to our catalogues, appeared to indicate a red dwarf star approximately 42 light-years from Earth in the constellation Ophiuchus. The star had no common name, just a catalogue designation, LHS 1140. It was an unremarkable star by most measures, cooler and dimmer than our Sun, but it was known to have planets, including at least one rocky world in the habitable zone where liquid water could exist. if the interpretation was correct. 3I Atlas had traveled 42 light-years to reach us. A journey that even at a tenth the speed of light would have taken over 400 years. The probe was ancient, had been traveling through interstellar space since before the Renaissance, before Columbus, possibly since the Middle Ages or earlier. It had crossed the vast gulf between stars, carrying whatever mission its creators had programmed into it, surviving the cold and radiation and loneliness of the void, arriving here in our time to fulfill its purpose. The revelation that we could potentially identify where the probe came from, that we knew which star had a civilization capable of launching interstellar missions, was simultaneously thrilling and terrifying. It made the alien intelligence real in a new way, gave it a location, a context. Somewhere out there, 42 light-years away, orbiting a dim red star, there was or had been a civilization capable of building 3I Atlas. Were they still there? Had they sent probes to other stars too? Did they know yet that their probe had reached us? Or would it be decades more before our radio signals and their probe's transmissions covered the distance back to tell them? These questions occupied the minds of scientists and philosophers, and ordinary people around the world, as May began and 3I Atlas itself, the primary object, continued its relentless journey toward Jupiter. The secondary object, having completed its Earth encounter, was now receding, moving on a trajectory that would eventually take it out of the inner solar system. Some proposed sending another mission to follow it, to maintain contact, but the distances were becoming prohibitive. We had learned what we could from the close encounter. Now attention turned back to the main event. 3I Atlas would reach Jupiter in late June, about 8 weeks away. The solar panels, or whatever the deployed structures were now fully extended, creating a cross-shaped configuration visible in telescopes as a distinct asymmetry in the object's appearance. The power collection capacity, if Dr. Torres's estimates were correct, was enormous. The probe was charging up, preparing for something. Speculation about what it would do at Jupiter ranged from the mundane to the extraordinary. Perhaps it would simply observe the planet, study its atmosphere and magnetosphere and moons, gathering data to send back to its creators. Perhaps it would deploy more secondary objects, sending them to explore Jupiter's diverse family of satellites. Perhaps it would use Jupiter's gravity for one final slingshot, either to accelerate out of the solar system or to settle into a long-term orbit where it could observe for years or centuries. Or perhaps it would do something we couldn't predict, something that would only make sense from an alien perspective with alien goals. That uncertainty, that fundamental unknowability of what came next, hung over all the preparations and observations and analyses. The Juno spacecraft, which had been studying Jupiter for years, was being programmed for the encounter. Its orbit would bring it relatively close to 3I Atlas during the crucial period, and every instrument it carried would be focused on the interstellar visitor. We would gather data, the best data yet, and maybe, finally, we would begin to understand what this thing was and what it wanted.